Welcome back, everybody, to our H0 2020 ESO online conference. So again, I'm Antoine Méran. I was the host on Tuesday, and I'm the host today for this session on day 4. So just a quick reminder. So this is the program for today. Yeah, sorry, I had the YouTube running at the same time. So this is the program for today. We're moving closer to we go back in time, closer to the CMB and closer to cosmological measurements of H0. And as well, we're going to go also address possible explanation for the tension in the H0 measurements. We'll later have a panel discussion as well with Pablo Lemos, Matthew Colles, Norma Sanchez, and Levon Pogosyan. So I highlighted on the right the Q&A link that you can find on the program, and this is how you ask questions. If you haven't been participating in the previous days, this is how it works. We use a platform called Slido. So this is how it looks. When you click on this link, you will be brought to this page. And on the top, you can ask a question. You have the option to leave your name as well. And below, you see the question that you can upvote, and the highly voted question will actually be asked during the conference. So for the speakers, a reminder, you just have to listen to me at the end, and it will ask the question. Just remember to run the chat on Zoom, so I can remind you of the 5 minutes and 1 minute warning before the end of your talk. I also want to let you know that we're using Slack also for offline discussion. So a few aspects I want to point out for today. If you go to the #questions channel, this is where you can find the speaker's answers to Slido questions. So these are the questions that are not answered during the session, but because of lack of time, so the speakers kindly answer to this question offline. We also have a new feature today. You may have seen if you are on Slack that we have a post-conference poll that is posted by Richard and is now available on the channel announcements. And we kindly ask you to fill it up because we would like to know how you found the conference and how if you have any feedback for us. If this is not enough, you can also use the channel Ask the Lock, where you can freely talk to us. Actually, I would like to ask also people who have participated in the question channel, answering questions for the speakers or participating in the discussion for our participants, if you are not comfortable with us publishing later these discussions. So please let us know as soon as you can. Go to Slack, Ask the Lock, and let us know if you disagree with us posting later on these discussions about the questions that were asked on Slido and answered there by the speakers. So with that in mind, I will stop sharing my screen now, and I think we are ready to move to the first talk. So I don't know if Hendrik Hildebrand is available. Yes, he is. So you can share your screen now.
Sure.
Okay.
Can you see my screen?
Yes, we do, and we hear you.
Very good.
Okay, you can go ahead.
All right, good afternoon, everybody. Great pleasure being here. Thanks for the invitation. So we're changing gears a little bit now. I'm supposed to talk about gravitational lensing, weak gravitational lensing to be precise. We're not measuring H0, so you might wonder, what am I doing here at an H0 conference? I guess the reason I was invited is that we also see some tensions when we measure weak gravitational lensing, and these tensions are also with respect to the Planck measurement. So this is potentially very interesting. But before I show you these results, let me start very basic with a sketch that describes what we're doing and why we're doing this. So in weak gravitational lensing, and in particular, I'm talking about cosmic shear here, we're using images of the sky where we measure the ellipticities of galaxies and try to infer something about large-scale structure. And the way this works is, if you start off with some galaxies that send out some roughly elliptical light bundles, these light bundles travel through the large-scale structure of the universe, get continuously deflected by all structures there are on the way. And not only do they get deflected, but they also get distorted because gravitational lenses are, optically speaking, bad lenses, and they introduce distortions to these light bundles. So if you start off with a sample of galaxies whose light bundles are randomly oriented, and why wouldn't they? Galaxies are pointing in random directions on the sky. Once the light bundles have traveled through a large-scale structure, they are actually not randomly oriented anymore. Through these deflections, light bundles that travel nearby each other will have a tendency to point in the same direction because they were distorted in a similar way. And that's exactly the signal we are looking for when we measure cosmic shear. Now you might wonder, why is this different from other cosmological probes that use galaxies, like galaxy clustering, for example? The most important difference here is that we do not use the galaxies directly. We are not really interested in what the galaxies are doing. We're just using the galaxies as convenient light bulbs that yield these light bundles for us. So we have a pretty direct way to measure the dark matter structures, and hence with this measurement we're sensitive to the statistical properties of large-scale structure, but also to geometry, because these light bundles travel over a long time, and that gives you some information on the expansion history. So from an observational side, what you need to do is you need to measure the ellipticities of many, many galaxies from high resolution images. Then you also need some distance estimate, and since we're talking here about many millions of galaxies, this has to come from photometric redshifts. So these are our main observables, and these are also where our observational systematics potentially can creep in. If you've done all of this, what you get is called a two-point shear correlation function. So this is a typical measurement shown here. So this is really a quantity that measures how strongly galaxy ellipticities are aligned, or in other words, how strongly galaxies are pointing in the same direction as a function of their separation from each other. So the way this works is you take your image, extract all the galaxies from these images, and then look at all pairs of galaxies at a given separation and check how strongly are they pointing in the same direction. It's a very small signal, hence the small numbers on the y-axis, but if you have large samples of galaxies, many millions of galaxies, then you can pull this out from the data. The nice thing about this signal is that it's very directly related to the matter power spectrum. That's really the strength of cosmic shear. So this is the estimator, that's what we're observing. So you average over pairs of galaxies and average their ellipticities. And you can pretty directly relate this to the matter power spectrum. You basically need two integrals, a line of sight integral here, where you integrate over the redshift distribution of these galaxies, which is this quantity down here. And then you need another integral to do a Hankel transform. You can also estimate the Kappa power spectrum here directly, but I'm not going to talk about this. The nice thing about all of this is that there's basically no astrophysics in here. So once you have the power spectrum, and that might involve some astrophysics, but I want to sweep that under the rug for now. Once you have a power spectrum, it's really very simple. So it's pure GR, so to say. There's a complication with the redshift distribution that you have to estimate and put in, and that's where you can also get errors, systematic errors on your model side. But the great appeal of this technique is really that it doesn't depend on galaxy biasing. And that also means you can push to much smaller scales. When you do galaxy clustering for cosmological purposes, you typically stick to quite large scales because you're worried about linearity and stochasticity of the galaxy biasing. With cosmic shear, you don't have to worry about this. You can push to smaller scales. At some point, you also get worried about how well can you model the power spectrum, but that's a different topic. If you have redshift information from your photometric redshifts, you do not do just one measurement, but you split your sample up into redshift bins. You have to estimate a redshift distribution for each of these bins. An example is shown down here, where 5 bins were used. And then you can estimate these shear two-point correlation functions for all the bins separately. There are two flavors of this these correlation functions, psi plus, shown here on the top left, and psi minus on the bottom right. That's just because the ellipticity is a two-component quantity, so we have two flavors of correlation functions. And these are what we call the autocorrelation functions here on the diagonals. So you really do a measurement for each bin separately. But if you have these bins, you can also, when you form your pairs, take one galaxy from one bin and the other galaxy from the other bin, and then do cross correlations. And this is all the cells here that you see on the off diagonal. And all of these cells contain somewhat complementary cosmological information. In particular, the relative amplitude of these different cells tells you something about geometry, but also how structures evolve over time. So this is something that's often not appreciated because these signals look relatively smooth, featureless, but it's really the relative amplitudes that contain a lot of information. All right, there are currently 3 experiments, 3 surveys that are trying to measure this cosmic shear. This is the Dark Energy Survey, Hyper-SupremeChem, and the Kilodegree Survey that I'm involved in. And they're all trying to measure cosmic shear. These are so-called stage 3 surveys. But they approach the whole thing from slightly different angles. They put an emphasis on different things. So Hyper-SupremeChem, they have the largest telescope. It's the 8-meter super telescope. So they can go very deep. They have many galaxies per area on the sky that they can measure an ellipticity of. And they also have very sharp images because they're in a very good location. The Dark Energy Survey, they have the largest camera, so they will, in the end, observe the largest area on the sky, have the largest cosmological volume, which really helps with your sample variance. And then there's us, the Kilodegree Survey. The nice thing about the Kilodegree Survey is that there is a sister survey called Viking, which covers the near-infrared. So we're basically the only survey combination which observes over a wider wavelength range, going all the way from the near UV to the near infrared. Also, the telescope that's being used for kids is a dedicated weak lensing telescope with a camera in the Cassegrain focus, which gives you a very nice point spread function, which you need to correct for when you want to measure galaxy ellipticity. So that's good to start with. All right, each of these surveys will in the end cover hundreds of millions of galaxies. So these are large data sets. Actually, the observations for KIDS and for DES are already done. HSC is still observing, but all of these surveys are still doing their science analysis. So currently we only have science analyses that are based on at most a third of the data from these surveys. And that's what I'm going to talk mostly about now. So here's a summary plot that shows you typical cosmological constraints from these stage 3 surveys that are the best cosmic shear constraints that there are currently. So on the left-hand side, you see omega matter versus sigma 8, and you see this typical banana degeneracy shape. So cosmic shear basically cannot distinguish whether you have a lot of matter that's weakly clustered or you have little matter that's strongly clustered, hence the degeneracy. And that's why we usually look at this parameter S8, which just combines these two, sigma 8 times square root omega matter scale to some fiducial value. And then you get these nice, almost horizontal constraints here, depending a bit on your redshift range. Overplotted are also the constraints from Planck legacy in red. And you see 2 things. First of all, you see that all these weak lensing surveys agree with each other. So they're quite consistent. All of them yield an S8 that's lower than the S8 value from Planck. Now, whether this is serious or not depends a bit in which camp you are. Whether if you're a member of the Dark Energy Survey, you would probably say, this is not significant. This is almost agreement. Now, I'm a member of the Kilodegree Survey. I might be a bit more worried because our measurements are 2.5 sigma away. So what's the story here? What's going on here? And to understand this, it's very important to look into systematic errors as in each field of research. And there are a long list of systematical errors, but these are the most important ones, I think. So on the observational side, we certainly have the shape measurements. We need to measure accurate ellipticities for tens of millions of galaxies. And these are quite sophisticated algorithms that have to correct for the point spread function and get a very small bias on average for such a large sample of galaxies. And these are faint galaxies. These are fuzzy little blobs, right? Same is true for the redshifts. You need to get the mean or the average redshifts of these galaxies extremely accurate to not bias your measurements. Again, you're not so much interested in very accurate redshifts for single galaxy, but rather in the ensemble of galaxies in the redshift distribution that needs to be known to very high accuracy. And there are also problems on the theoretical side. This basic assumption that galaxies are pointing in random directions is not quite true on small scales. There are tidal effects that actually align galaxies with each other, and you have to take that into account. That's typically called intrinsic alignments. And as I said, once you have the power spectrum, everything's easy. But yeah, to get the power spectrum, you also have to take into account baryons, because unfortunately our universe contains baryons. So you need to understand baryon feedback, and our understanding of baryon feedback is not very good at the moment. So you have to marginalize over a large number of scenarios there. Over the past few years, I think a lot of focus has been given to the redshift distributions, because this is potentially at the moment the most serious of these systematic errors. And that's why I want to talk about this in a bit more detail. Going back to this plot here, it's interesting that the two surveys that are a little bit closer to Planck, HSC and DES, do something quite different for the redshift calibration than the survey that is a bit further away. It's the kilodegree survey. So I already told you the kilodegree survey has near-infrared data, which the other two surveys don't have. So in principle, the redshift should be a bit better. But you also need to calibrate your redshift distributions. And the way this is done is different in these three surveys. DES and HSC, they use the Cosmos 2015 high-quality PhotoZ catalog to calibrate their redshifts, whereas in the kilodegree survey, we are using spectroscopic redshifts. And you might wonder, does any of this actually play a role? And I think the answer is yes, it plays a role. We actually took the public DES data and tried to calibrate them in a similar way as the KIDS data. And when you do that, your S8 actually goes down by almost a sigma. So here in dashed, you see kind of the original DES constraints, and in blue, you see the recalibrated ones when you use spectroscopic redshifts. Now, we had a lot of discussions about this with our colleagues from DES, and I think we all learned a lot from this. And I'm not claiming that one of the two alternatives is the right one and the other one is wrong. So this is really very active research at the moment. Both have pros and cons, but whether you're claiming attention to with respect to Planck or not really hinges on that question. So this is really where a lot of work is going currently into in these surveys, in these survey teams. So let's for a moment assume the blue one is the correct one. Then you have put KIDS and DES on the same calibration, and you can combine the two, and what you get then, pretty tight constraints in this omega matter S8 plane. These pink constraints that you see here is the combination of the two. And then you're actually in more than 3 sigma tension between these combined weak lensing constraints and Planck. So that's a recent paper by Marika Asghari, where I think for the first time we passed this quite crucial 3 sigma threshold for the discrepancy between these different cosmological measurements. Whether this is true or not, I think there's still the question mark about the redshift distributions and a few other question marks. But yeah, as I said, we're all working on this to get this more rock solid, potentially. One way of doing that is actually to reduce your source sample. It sounds a bit counterintuitive, but if you can identify the sources, the galaxies that are used for the weak lensing measurements, where calibration is worst, and throw these out of your sample, you should end up with a more robust redshift calibration. And there are actually ways to do that. You can take your high dimensional magnitude space, 9 dimensions in our case, because we have 9 bands from KIDS and Viking, and map this out into the plane with a self-organizing map. This is shown here on the top right. And this map is now colored by which calibration sample is used to calibrate this galaxy, basically. And there are also some black spots where we don't have calibration galaxies, and these you throw away immediately, but you can also check for each pixel of this map whether the properties of your source sample and your calibration sample match. And if they don't match, you also throw out these sources. And by doing this, you can cull your source sample. And we did this, losing about 15% of our number density, and then redid the whole cosmological analysis. That's what we call our gold sample, as a paper led by Angus Wright. And the constraints from this gold sample you can see here, not quite in gold, in orange, in comparison to the original constraints, which are these dashed dotted contours here. And you see very little change, actually. So the redshift distribution change, your correlation functions change, but the cosmological constraints pretty much stay right put where they are. There's also been a lot of discussion about the deep 2 sample. We took this away from our calibration sample, threw away all the sources that are calibrated by deep 2, and then we get the green constraints. So also this lies right on top of the other measurements. So we think that the KIDS calibration at least is robust. Whether this is true for DES calibration, we cannot say. When we calibrate DES with spectroscopic redshifts, we only have a 4-dimensional magnitude space, which makes things much harder. All right. Yes, I think I'm pretty much the only talk speaking about this tension on S8. Thought I'd show this plot here by Ian McCarthy. It's already a few years old, but I think the whole picture hasn't really changed. This is again omega matter versus sigma 8, but now for different cosmological probes. So cosmic shear, what I've talked about so far in the top left, cluster counts from TSZ, top right, galaxy clustering, galaxy-galaxy lensing, bottom left, and CMB lensing in the bottom right. Planck, this is Planck 2015, is shown by the black circle. And you see a pattern. Basically, all late universe large-scale structure measurements yield an S8 that's smaller than Planck. That's very similar to the situation with H0, just the other way around. No late universe H0 measurement gives you an H0 smaller than Planck. So this is intriguing, at least. So you can certainly assign some significance to it and say, are there models that actually alleviate this tension? And we played that game in a paper that's already a few years old. The only model that we could find in this list that you see here that alleviates the tension and at the same time is preferred by the data in an Occam's razor sense is a phantom dark energy model. Yeah, whether you like phantom dark energy models or not, when you're in this part of parameter space for W0, WA is a different question. I'm sure we'll discuss this later in the panel. But yeah, this is just what the data say. All right, can you do any better than this? Well, you can do better by combining cosmic shear with other large-scale structure probes. And this is from a very impressive paper from the Dark Energy Survey, where they combined the cosmic shear measurements that I talked about so far with galaxy clustering measurements and galaxy-galaxy lensing measurements. And then you gain a lot of statistical power, and you also gain a lot of degeneracy breaking power. And the constraints are shown here. This is omega matter versus S8. The cosmic shear only constraints, what I showed you before from the Dark Energy Survey, is now shown here in green. And the two other probes are shown in red. If you combine the two, then you get more than the sum of the parts. And that's shown in blue. You get a pretty tight constraint on the matter density, actually. I also wrote down here that the green one is not affected by galaxy bias, whereas the red ones are affected by galaxy bias. There you need to assume a bias model and marginalize over these parameters. But when you combine them, actually the cosmic shear can cross-calibrate these bias parameters. So this is really where you want to go. We also did this with KIDS-VIKING, combining with BOSS. That's a paper led by Tilman and Tröster. That also shows a pretty significant tension with respect to Planck, at least when you look only at S8, and then you're also at the 3.5 sigma level. However, when you combine these different large-scale structure probes, you start constraining other parameters, not just S8. And then you certainly also have to look at these other parameters. And if you look at the full parameter space, the tension is more like at the 2 sigma level. If you've seen BOSS constraints before and wonder why are they so low compared to Planck, that's because we're sampling here in lambda CDM parameters and not in the geometric BAO parameters. So what's next? I mean, all these surveys have more data on disk and are currently analyzing this. Later this year, we'll see DES year 3 analyses. We'll see KIDS 1000 analyses. Not sure if we see anything from HSC. I don't have information on that, but the data release 2 from HSC is also twice as big as their first one, and has been public for a while. The big question is, can systematic error control keep pace? For kids, I think we can answer this with a yes. So we've done some predictions of how well we will do with KIDS 1000 compared to kits of Viking 450, and that's what you see here. So it's pretty much exactly a root 2 improvement in the constraint on S8. Certainly these are forecasts, so where these green contours lie, we don't know yet, we're still blind. Same is true for 3 times 2 point. If you combine KIDS 1000 with the BOSS measurements, you also get a root 2 improvement. So it will be very interesting to see where these contours lie. So my time is up. Let me summarize. Cosmic shear is one of the cleanest probes of large-scale structure because it doesn't depend on galaxy bias. Current surveys constrain S8 with CMB-like precision, and basically all of them, and also other probes of large-scale structure at low redshift, give you an S8 that's smaller than the one from Planck. Some measurements even at 3 sigma. However, the redshift calibration is really crucial. This looks a lot like H0 a few years ago. Let's see with the new measurements that are coming up this year whether we'll stay on this course. So thank you.
Well, thank you, Hendrik, for this insight in yet another tension. So we have some questions here I'm going to ask you. So the first one is from Richard Anderson here at ESO, and he's asking, is Planck measuring the same observables as KIDS/HSC/DES to determine sigma 8?
I'm not sure what Richard means with observables. Certainly, it's completely different 2-point statistics, right? We're using galaxy 2-point shear correlation functions at redshift below 1, basically, whereas the CMB constraints that I showed you are temperature and polarization and isotropies of the CMB. So these observables are certainly very different. We're sampling in essentially the same parameter space. So we're sampling in lambda CDM parameters. Not sure if that answers the question.
Well, I guess Richard will let you know on Slack if he's not happy with the answer.
Sure.
So the next question is by Samuel Braden, and he's asking, does the H0 tension propagate into the sigma 8 tension through the choice of units in the sigma of R definition?
Not really. I mean, we sample over the Hubble parameter when we do our weak lensing measurements, but we're actually not constraining the Hubble parameter. So we typically put a broad prior on this parameter that encompasses the Planck as well as the Schu's results, and then marginalize basically all that parameter. The S8 tension is really not affected. You could also put a tighter prior on H, whether you center it on Planck or on Schu's doesn't really affect the S8 tension. You will pretty much get the same results.
Okay, so the next question is an anonymous question, and it is, in the combined KIDS-HSC/DES showing the strongest constraints, omega m seems also quite low. Is there some tension there too, perhaps with Planck, SN1A, and BAO?
Yeah, that's right. So I should say this combined constraint here, this does not include HSC. We couldn't do the spectroscopic calibration for HSC because HSC is very deep. You basically don't have a spectroscopic catalog that's deep enough to calibrate HSC. So it's not going into these joint constraints that you see here. But you're right, there's also quite a displacement in omega matter here. It's more like at the 1.5 sigma level, I would say, by eye, if you projected this on the omega matter axis. But yeah, there's something there. In general, I think we shouldn't look at 1D or 2D constraints. With these kind of combined constraints, we really have to look into the full parameter space because this makes quite a bit of a difference, as I showed here on this slide, whether you're talking about 3.5 sigma tension when you just look at S8, or you get 2 sigma tension when you look at the full parameter space. Cosmic shear alone basically just constrains S8, but if you fold something else in, then it becomes more tricky.
Okay, I think the time is up for the question, but thank you very much for answering the questions. Please follow up on Slack if you can for the questions that were not answered, and we can move to the next speaker, who's Nathalie Palanque de la Brouille. who is going to talk to us about baryon acoustic oscillations with DESI. Natalie, if you can hear me. Okay, I see the slides.
Yes, so do you have the slides?
We can hear you.
Okay, and you have the slides also?
Yes.
Okay. So I'm Natalie Palangde-Abreu from CA in France, and I also want to thank the organizers for this invitation and for organizing this really remarkable conference. I've been asked to present BAO in the context of DESI. So I'll start by doing that, and then I will explain how BAO can constrain H0. So I'll give for this constraint on H0 the most recent results, and I'll show the improvements that can be expected with the upcoming of data from the DESI experiment. So just to reset BAO in its context, where does the BAO signal come from? The propagation of photon baryon over densities in the early universe gives rise to the well-known CMB anisotropies. Because of Compton scattering, the baryons are carried over with the photons, and thus this trace similar anisotropies as what the photons do at the epoch of recombination. The characteristic size between the location of the initial overdensity where the CDM remained and the distance to where the baryons have been carried over is defined by the sound horizon. So it's a distance of 150 kiloparsec at recombination, which today has evolved under the expansion of the universe to a characteristic scale of 150 megaparsec. And because we expect the galaxies to form in the peaks of these density waves, we can expect to find that same characteristic scale in the typical distance of separation between galaxies on the sky. And so this is a very large scale, 150 megaparsecs, so it doesn't show when we look at a typical distribution of galaxies, and it has to be measured statistically. So what we use to measure the BAO feature is a two-point statistics, like we've just seen with lensing. So this is an artistic view. Of course, we do not see the rings of overdensities, but what we do, we take every galaxy and compute its two-point statistics with every other galaxies in the universe. We can do that in two ways, either in real space where what we compute is correlation function, and there we expect to see a peak in that distribution, or we can do the same in Fourier space where what we compute is the power spectrum, and when we divide by the smooth power spectrum, this peak shows as wiggles in the power spectrum of the two-point statistics. This is the simplest method. We can go to higher order statistics, but all the information is there already. BAO was first measured in 2005, but we now have an over 8 sigma detection of the BAO feature using a single experiment, so just from BOSS. What we measure with BAO is not directly distances, it's angles and redshifts. So to convert that to distances, we have to use a fiducial model, and we quantify the departures from this model using a factor alpha, which is just a ratio of what we measure to what is predicted in the fiducial model. So we expect alpha to be equal to 1. And I'm here just showing two examples with two different sets of galaxies that were measured with BOSS. And you can see that the precision we now have on this distance measurement, the BAO feature measurement, is at the level of about 1%. So we can compare this BAO isotropic measurement to what is predicted from Planck using a lambda CDM cosmology. This is a plot that's extracted from the Planck 2018 cosmological paper. The gray band is the prediction. Well, the line is the prediction. The gray band are the 1 and 2 sigma uncertainties around this prediction. And you can see that the isotropic BAO measurements are all in very good agreement with the predictions that we have from Planck. However, BAO is a 3D measurement, so we can go beyond an isotropic measurement. We can have two different sets and independent sets of information. Transversely to the line of sight, we are measuring an angle which is directly related to the angular diameter distance dA of Z. So that's similar to what we can obtain with type 1a supernovae, where we measure the luminosity distance. Along the line of sight, so in the radial direction, what we measure are redshifts, and the delta Z, the difference in redshift under which we see the BIO feature, is directly related to the Hubble parameter H of Z. And so here we have direct measurement of the expansion rate of the universe at the redshift of the sources we're using to measure that BIO feature. This plot illustrates the status of the current results on BIO from the various successive BIO data releases, as well as prior BIO data sets. It illustrates the Hubble expansion rate as a function of redshift. So time flows to the left, oopsie, on this plot. And what is quite nice is that we can see in this kind of plot the deceleration of the expansion rate of the universe as long as the universe was still matter dominated, and the recent acceleration that we're currently undergoing when the universe is now dark energy dominated. So this is the current status. What we want to achieve is to go from this type of measurement to this one, where we can really cover the entire history of the expansion rate of the universe with percent or sub-percent level measurement out to a redshift of about 3.7. And this is precisely the goal of the DESI experiment. So DESI, which stands for Dark Energy Spectroscopic Instrument, is a pretty large project. It's a collaboration of over 650 people coming from 74 institutions worldwide, over half of them being non-US, and Europe has a significant part to play in the DESI experiment. It's a stage 4 experiment, so it means a factor of merit of improvement of at least a factor of 3 compared to stage 3. And to do so, we rely upon 2 techniques, the BIO approach that I've presented, and also redshift space distortions, which I won't have time to describe in this talk. The uncertainties scale with inversely with volume and proportionally with inversely rather with the volume density of our sources, which means that to improve on the uncertainties that we want to achieve with DESI, we can play on these 2 key parameters. So we can increase the volume density of our sources to the level where we reach product n times p, where p is the clustering power, about equal to 1. Going beyond that is useless, because then it's more interesting to increase the volume. But below that, we would be dominated by the galaxy shot noise, which we want to avoid as much as possible. We also try to maximize the volume, and for that we're planning on a footprint of 14,000 square degrees, which is basically the entire extragalactic sky that can be observed from a given point on Earth. And in terms of redshift coverage, we want to aim for redshifts all the way out to 3.7, which means covering about 12 gigayears in the history of the expansion of the universe. To do so, we will rely upon 5 classes of sources, and that have been chosen so that we can obtain easily the redshifts over a broad redshift range. And we've also ensured that these different target classes overlap in redshift, so that we can check the results that we obtain in these redshift overlap regions, but we can also do some cross-correlation analysis, which significantly improve the uncertainties on the final measurements. So these are the different target classes that we're aiming for. So in the very local universe, we'll use 10 million very bright galaxies that are bright enough that we can observe them in what we call the bright time. So that's when the moon is up. And then going away from the local universe, we'll use 6 million luminous red galaxies, similar to what was done in BOSS. Then the bulk of our sample will consist in 17 million emission line galaxies. These are young galaxies that have very bright emission lines and that can be seen out to pretty distant redshifts, out to about 1.6. Beyond that, we'll rely upon quasars, which we'll first use as direct tracers of the matter when they're abundant enough. And then in the most distant universe, we'll use quasars as background lighthouses to illuminate the intergalactic medium along the line of sight. And the absorption caused by the lamina far forest on the line of sight will be the proxy we'll use to test, to measure the clustering of matter in the universe in this very distant universe. In total, we expect to obtain the redshifts of 35 million sources, which is about a factor of 20 more than any redshift survey before DESI. Hardware-wise, DESI is pretty remarkable also. I won't go into the detail of the instrument. I just want to mention that it's using the 4-meter Mayall telescope in Arizona. And except for that primary emitter, which was already existing, pretty much everything else in this instrument has been entirely refurbished for the purpose of DESI. So we have design and built a wide field corrector so as to reach the large field of view that is required to have the large footprint that we want to be measuring. This was built mostly in England, and you have a picture here of the lenses before being mounted into the corrector. It's 6 lenses that are over a meter in diameter. It's really huge. And the image you have here of the Whirlpool Galaxy was obtained on the first night where we turned on this the corrector, and it showed that we can obtain sub-arcsecond images of the entire field of view of the camera, which is quite remarkable and a big success for that corrector. At the other end of the light path, of the photon path, you have the spectrographs. We have 10 spectrographs which are located in the temperature controlled room for best measurements. And the light in these spectrographs is split into 3 different channels, 3 different bands, going from the UV so that we can measure the lamina forest absorption down to a redshift of about 2, up to the near infrared, so as to be able to measure the O2 emission doublet from the ELGs out to a redshift of about 1.6. And this is the spectrum of one of the first ELGs we've been able to observe during commissioning. And that spectrum actually comes from the last night when we could use our telescope before the shutdown due to COVID. And finally, last but not least, the focal plane of our instrument is equipped with 5,000 fibers, which are each mounted on a robotic fiber positioner. So you see here the motion of these fiber positioners, which can relocate the fiber within about 1 minute to where we want to be observing on the sky. And this is a significant improvement compared to what was done in SDSS, for instance, where it took about an hour to manually plug each of the fibers into the aluminum plates that were previously drilled at the location of the sources we wanted to observe. So what does DESI and more generally BAO do for H0? So this is the Hubble diagram, Hubble expansion rate as a function of redshift that I've shown before, showing the expectations that we want to reach with DESI. I've illustrated here the different target classes that we want to be measuring, observing, and so you can see the overlaps in terms of redshift between these different tracers. And these are the uncertainties that we want to achieve. These are our requirements on the isotropic BAO measurement, as well as in the very distant universe, the uncertainties on the expansion rate of the universe. All of them below the percent level precision, at better than a percent level precision. How do we go from BAO to H0? As I've said, BAO doesn't measure distances. What it measures are angles across the line of sight and redshifts along the line of sight. So with angles, we actually have a handle on the ratio of the sound horizon to the angular diameter distance. And with this redshift size, we have a handle on the ratio of the sound horizon divided by C over H. So you see that whatever approach we take, what we need to calibrate our data is a measurement of the sound horizon. This is mostly dependent on the baryon density omega b, and a little bit also on the density in cold dark matter. So what we need is a measurement of omega B. This can come from two origins, either from CMB, and I'm here showing the latest measurement of omega B from Planck 2018, but it can also come independently from the theory of Big Bang nucleosynthesis, to which we add, so the predictions of BBN, to which we add measurements, for instance, from the recent deuterium-2 measurements. And here are the uncertainties that we have on omega B coming from this technique. So once we have the standard horizon distance, we can infer h of z, so either from this or from the integral of h of z. And to go from h of z to h naught, we actually need to distinguish the information coming from h naught from that coming from the cosmic evolution, and in particular omega n. However, one of the big interests of BAO is that we have a pretty large lever arm in redshift, and so we can really distinguish the impact of h naught from the evolution history that it's embedded in omega m of z. And so in particular, if we use the measurements at low redshift, so typically below 1, where dark energy dominates, and compare that to the measurements at high redshift, above 1 typically, where dark matter dominates, we can really get a result that is basically insensitive to the cosmic history, and thus infer a pretty stringent result on h naught. So what I'm going to show now are the most recent results that we get on h naught from BAO. These are not yet published. It's really a teaser for papers that are about to come out within a few weeks. We're hoping to have them on archive by July 20 of this year, so in 3 weeks from today. These are coming from the EBOS DR16 BAO analysis, and I'm here showing the h naught constraints that we expect, that we obtain from this new data set as a function of omega m. The two sets of ellipses show the low redshift measurements, so where dark energy dominates, and the high redshift dominance, high redshift results where dark matter dominates. And these are obtained with galaxy clustering, and these are obtained with quasar and Lyman alpha BAO information. So there are two things to notice. As I've said before, the degeneracy angles are pretty orthogonal to one another, so it's very interesting to have this large lever arm in redshift. With the DR16 results, these two ellipses overlap very nicely. They're in very good agreement, which is a significant improvement compared to what we have in DR14, where there was a small tension between the low and the high redshift measurements of BAO. And so combining these two sets, we have a very good determination on h naught at the level of 1.0 using BAO information alone, here combined with Big Bang nucleosynthesis. I'm here giving the expectations that we have for DESI, so the forecast. We expect to keep on improving on these uncertainties down to the level of 0.2, well, 0.19 for fixed mu using Planck and a lambda CDM model. And this loosens to 0.27 uncertainty on h naught if we free the neutrino masses. So summarizing all these results, I'm here using a plot from Licia Verde, which is updated to include the two of the most recent EBOS DR16 results. So in gray, you have the result that we obtain for BAO, low and high redshift, plus BBN in lambda CDM model. The central value is in remarkable agreement with what is obtained from Planck, and the uncertainty is at the level of 1.0, as I said before. I've also mentioned that this result is pretty insensitive to the cosmic evolution that we assume, and to illustrate that, we've also computed the value of h naught that we obtain in an open W0 WA CDM cold dark matter model. So this is a pretty flexible cosmic evolution. We're here using BAO plus CMB plus supernovae, and you can see that the central value is barely affected, and the uncertainty here is still at the level of 0.9, so pretty unaffected also by the loosening of the cosmic evolution that we're assuming. So these are the two results shown here. I'm also illustrating the forecast from DESI. So here, of course, the central value is meaningless. That's the forecast. But what you have to appreciate are the small error bars that we expect to be achieving with this upcoming DESI experiment. And so here are my conclusions. I just want to insist on the fact that BAO can provide a pretty tight constraint on H0, even though it does not measure directly H0. This comes from this inverse distance ladder approach, so going from high redshift universe and propagated down to low redshift. It's mostly insensitive to the model of cosmic evolution that we assume, thanks to the large level arm redshift that we measure with BAO. And it can provide a measurement of H0 that's independent of CMB if the sound horizon is determined instead from BBN, Big Bang nucleosynthesis, and a measurement of deuterium. So I'm here recalling the two most recent values that we obtained on H0 from the DR16 EBOS papers that will come out in a few weeks. And here we're calling the forecast that we expect to be achieving with DESI. Thank you.
Well, thank you, Nathalie, for this very exciting new result you shared with us in advance of even the preprint. So it's very exciting for such a conference to have a result like this. And also thank you for the very exciting prospect of DESI. I'm looking forward to this plot with the real value of H0 you get. It's going to be very interesting and potentially increase a lot the tension. So let's go to the question. So the first question on Slido is an anonymous question. You said the BAO ruler is physically 150 megaparsec. Doesn't that depend on whether it's calibrated by the CMB, early universe lambda CDM dependent, or late universe?
Yes, of course, because this 150 megaparsec is assuming that we take the history of the universe from the early universe, so assuming Planck cosmology. We can also compute the sound horizon on the other way around, taking the cosmic parameters from supernovae, for instance, and then we get a different size, and instead of 150, we get something more like 130 megaparsec. So I've here taken the standard flow of time to provide that 150 megaparsec information.
Okay. The second question is from Richard Anderson here at ESO. How come the current Lyman alpha measurements are so much lower than the fitted H of Z relation?
So these measurements move a lot depending on, well, move by a few sigmas depending on the data releases. They used to be in higher tension with the first measurements at about 2.5 sigma. This tension is reducing with time. I don't have the latest tension in mind, but I think it's something like 1.7 sigma only. So this is what we have currently, but then it's not a huge tension, and it's evolving as we keep on accumulating data. So we do believe that the initial tension was mostly a statistical fluke, and it's reducing with time.
Okay, thank you. I think we have time for another question, maybe two if you're fast. Different tracers like USO, LRG, ELG have different linear and nonlinear bias parameters. How do they compare at the same Z? Do they help in mitigating systematics? And that's a question from David Valls-Gabo.
Yes, and actually that's why we do want to have overlap in redshifts between the different tracers. The fact that we have different biases is quite interesting, and the cross correlation does benefit from these different biases. What did I want to say? We do calibrate them differently. I mean, we have different sets of mocks to analyze the data from the different tracers, so that we can take into account in the mocks the fact that these tracers have different biases. So this is all taken into account. We have no discrepancy that has been observed so far. And it's actually quite interesting to have these different approaches to BAO, as it helps checking the result, and it helps in the cross correlation of the different tracers. Okay,
I think I need to ask this question, even if we have only 1 minute. When will DESI achieve its full precision in measuring H0? How many years from the start of the survey?
So the survey is planned for 5 years. We will start, we finished commissioning. As soon as we can reopen the observatory, we'll have a 4-month survey validation where we have to finalize our target selection and our survey strategy. So basically that will carry us to the end of 2020, and then we'll have a 5-year survey to reach that full precision.
Okay, we can't wait. Well, thank you again. So now it's time to move to our next speaker, is Julien Lesgourg, who is going to talk about the sound horizons from Big Bang nucleosynthesis.
Yeah, so I think I cannot share before Nathalie.
Yes, I'm trying to unshare. Stop sharing. There we go.
Thank you.
So we hear you, Julien, and we see your screen.
Very good, thank you.
Please go ahead.
So this talk will partially rely on results obtained by my young collaborators, Thais, Manuel, Diana, Misha, Matteo, Niels, Michael, and of course, many more senior collaborators with permanent positions.
Oh, wait, Julien,
So,
we see the wrong screen. We see the presenter screen. So you should switch on PowerPoint. You should switch to...
Oh, yeah. Maybe I should just disconnect my external screen in this case.
Yeah, this is good now. Okay.
Fantastic. Okay, so despite being a big fan of the CMB and a member of Planck, I will talk about how you can measure H0 without using any information from the CMB spectra. And we will see, and already Nathalie started to show that there are many other ways to do so. So I will start from the expression, the well-known expression of the sound horizon angular scale. You know, it consists in this ratio of 2 integrals, and we should pay attention to the integral boundaries here. So if this theta represents the angle under which we see the CMB scale, the CMB acoustic peaks, then ZD and Z should be the redshift of photon decoupling. If theta is the angle under which we see the BA oscillation, then ZD is a bit different. It's called the redshift of the baryon drag time, and Z will be the redshift at which you have your galaxy or quasar data. Let's try to see how to relate this to H0 in a bit more details than in other presentations. To do that, you need to do a few assumptions. And to start with, I will do very general assumption on the thermal evolution of the universe. I will only assume standard scattering, standard recombination model, and that photon temperature scales like 1/A and is normalized to phi ras today. In this case, it's very easy and very robust to express the sound speed of the baryon photon fluid as a function of omega b only, and this ZD will also be a function of omega b, omega m, and the primordial helium fraction. To do further and see the role of H, we need to do a few more assumptions. And now I will assume something a bit stronger, that the universe only contains lambda, matter, and radiation, which includes the lambda CDM model and the model with free and effective. But we are already dropping the possibility of spatial curvature or late dynamical dark energy, which anyway have been extensively studied and are not, do not appear as very promising way to solve the Hubble tension. So with this assumption, we can replace H of Z using the Friedmann equation. And you see immediately that H0 is going to drop from the numerator and the denominator. So we will do this simplification. And for the purpose of having a nice formula, I will also simplify the numerator and the denominator by big omega m. And then what we get is this nice expression where we see that the integrals really depend only on the ratio between different components. Here we have the ratio between radiation and matter, which you can relate immediately with a redshift of equality. And here we have the ratio between the density of lambda and matter that you can relate to Z lambda, the other redshift of equality. And H0 is gone. So how come that theta is advertised as a way to measure H0? Well, it's simply because typically a cosmological model is not going to predict big omega r, but small omega r, the absolute radiation density, which you can normally relate to the photon temperature. And when you enforce small omega r to appear here, H now appears explicitly in the denominator of this term, and it also appears among the argument of this integral boundary ZD. So this is actually the precise reason for which you can get some information on H from theta, but you see that you need many measurements in order to do so. Now I'm going to be a bit more specific and talk only about the lambda CDM model, in which we fix a standard neutrino sector, standard BBN, and n effective close to 3. Later on, we are going, of course, to relax this assumption. And by doing so, we have a very nice expression now of our ratio theta, where we could replace omega r by something which is completely fixed by the CMB temperature. So we have no more 3 parameters here. We have only 3 free parameters left, which are small omega b, big omega m, and small h. Very good. So what can we do with this expression? Well, we need to fix omega b and omega m in some way in order to infer small h. So for small omega b, as Natalie said, a very nice way to fix it, if you want to be completely agnostic on the CMB side, is to use measurements of the primordial abundance of deuterium, which determines the time at which nucleosynthesis starts, and thus the yield of primordial deuterium compared to primordial hydrogen. So omega b is a parameter fixing this. So here is in these bonds, the blue and the green bond, what the prediction for the primordial deuterium fraction as a function of omega b. And we have 2 bonds here because there is an uncertainty on the nuclear rate, which is very important for nucleosynthesis. This uncertainty will disappear very soon because the nuclear rate is being measured currently by an experiment called Luna that will give its result very soon. So far we have a little bit of an uncertainty here, but you will see later that for our purpose of measuring H0, this uncertainty is playing an extremely minor role. Okay, so by using the measurement of deuterium, we have fixed omega b to some extent. And now to fix omega m, we have the choice between many alternatives without using the CMB. We can combine the BAO angular and radial or longitudinal information. We can combine measurement of theta as different redshifts. We can use information from distant supernovae. We can use information from CMB lensing or galaxy weak lensing, or we can use the full shape of the galaxy clustering spectrum. We are going to go through these possibilities in the next slides, but the overall message is that all of them will return a low H0 compatible with Planck, but in tension with direct measurements from shoes and others. And this really shows that we have this famous tension between early and late cosmology within the lambda CDM model. I should stress that in this talk, I'm only talking about early cosmology measurement. You could be confused because I'm talking of the galaxy spectrum of BAO. All these things are measuring quantities at low redshift, but they are sensitive to H0 through the sound horizon. And the sound horizon is imprinted in the matter-power spectrum at very early redshift. So really in this talk, we are only talking about measurement of H0, which have to do with the early cosmological model. Okay, so let's try to get H0 now by combining deuterium for omega b, the BAO angular information which constrains this expression, and the BAO radial or longitudinal information, which gives us a measurement of RS, the comoving sound horizon, over H at the redshift of the measurements. So this second ratio looks like theta, except that there is no more integral on the denominator. And thus, if you have the 2 information and you combine them, you see very easily that you become slightly sensitive to omega m. For instance, the ratio of the 2 is sensitive to omega m. Unfortunately, not so much. So when you combine BAO angular and radial information with deuterium, you get a measurement of H0, which is very correlated with that on omega m and with a big uncertainty. So it's not enough to give new information on the Hubble tension. But what is super interesting is that the direction of the correlation depends completely on the redshift at which you measure theta. And so if you want to reduce this degeneracy, you should, of course, combine different redshifts. You can see it, for instance, in this blue contour, in which you have already combined measurement of BAO from the radial angular information plus deuterium, putting together many redshifts between 0.1 and 1.5. you have reduced a bit the degeneracy along this direction, but you still get some very loose bound on H0, so not directly interesting. What you need in order to get more information is to combine measurement of theta at very different redshift. And for instance, you can combine this low ZBIO information with some high ZBIO information, for instance, from the Lyman alpha flux power spectrum in DR12 or DR14. In DR14, as Natalie said before, the measurements between high and low Z are not so much in tension anymore. You can safely combine them and you get a measurement of H0, which is in 3.6 sigma tension with shoes. Now, Natalie has superseded this plot by showing a teaser, which is really exciting, where I think that the equivalent contour is in higher tension with shoes. From what I saw in her slides, it sounds more like 4-5 sigma-ish. That's exciting. Still, if you don't want to trust this BAO Lyman alpha measurements, you have another option, which is to combine the low Z BAO with a measurement of theta from Planck. But now really you are not using the shape of the Planck spectrum, only the measurement of the angular scale at which you see the acoustic peaks. And then of course, since it's a measurement of theta at a very different redshift, you get a very different direction of degeneracy. And when you combine everything, you get a measurement of H0, which is in 3.8 sigma tension with a shoes measurement. Okay, one other way to reduce the uncertainty is to put extra information on omega m, for instance, from distant supernovae or from CMB lensing. In this case, you get contours like the green or gray one, which are roughly in 2 sigma tension with shoes. You can completely forget about using BAO Lyman alpha or the angular scale of the CMB peaks. You can try something different. You can try to use the full shape information from the galaxy correlation power spectrum or from the cosmic shear power spectrum. In this case, you have measurements of omega m and a few other parameters, which when combined with a low ZBAO and deuterium information are enough to measure H, in this case from the Desir 1 survey in 3.7 sigma tension with shoes, or in this very nice work by Phil Cox et al., where they fit the Boss full power spectrum with a very nice method. You get a completely independent measurement of H, which is still in 3.1 sigma tension with shoes. So we really have a problem. It's very exciting for theorists, and we are wondering what we should modify. The goal then, if you want to be still compatible with this BAO plus BBN bounds, is to find models in which you can higher the value of H while still getting the same result for the ratio theta. To do that, you can work out with the numerator or the denominator. With the numerator, for instance, you could try to add a new species in the early universe. If you do this, you will get an extra contribution to the bracket, and then you will get the same theta even if H is increased. And this is what you try to do when you try to solve the Hubble tension by increasing NF or putting some early dark energy. You could also try to change this boundary here, the redshift of decoupling of either baryons or photons. To do that, for instance, you could postpone recombination with a new ingredient changing the thermal history, some exotic energy release. There is a very nice recent paper of Yedamzik and Pogosyan in which they do this by assuming primordial magnetic fields in the early universe. If you want to stick to lambda CDM, the only way to change ZD would be to change the photon temperature today. But then if you want to solve the Hubble tension in this way, you need a rather extreme value of T0 that will be in conflict with phi-RAS. And even if you assume that for some reason you don't believe the phi-RAS measurement, we showed recently with Misha Ivanov and Yassin Ali Aimut that BAO and Planck data together are enough to constrain T0 up to a degree where you cannot play anymore with ZD, and you cannot reconcile the data lambda CDM with the Hubble tension. Okay, the other way is to play with the denominator. If you assume a different scaling in the denominator, you can hope that the denominator will change and you will need to compensate with a different value of H on the numerator. This game is extremely constrained. Vivian Poulin is going to say more about this in the next talk, but I think we can say that when you put all data together, this is essentially doomed to fail. At least this is my current understanding of the problem. Okay, so let's insist on the option of increasing NF here because it has another connection with BBN that I have not yet explained. If we start from our relation and we make NF a free parameter, we get another very nice and compact expression with now 4 free parameters. NF is now showing up in this argument because it contributes to determining YP together with omega B, and it is also a parameter of omega R. And if I increase NF, I increase omega R. So if I increase NF and I increase H at the same time, I will keep my ratio of radiation to matter fixed. If big omega M is also fixed, I keep the denominator fixed, and my theta is not going to change. So this is related to what I will call the overall scaling degeneracy. You have the possibility to increase simultaneously all the densities of radiation, matter, and lambda, and theta will be blind to this scaling. What will not be blind to this scaling is a measurement of H0, which has to do with the total density today. So you can get your large Hubble rate in this way, but also BBN. BBN will be affected because at early times you are changing the expansion rate, and this will modify in particular the prediction for the yield of helium compared to hydrogen. So if you use now some BBN data, not only on the primordial deuterium, but also helium fraction, you get some bounds on NF. NF must remain close to 3, and this will make it very difficult to solve the Hubble tension in this way, even without talking of CMB data. So you could see this in this plot, which looks like the previous plot of a few slides ago, but it's not, because here now we are still combining BAO and BBN data, but we have made NF a free parameter, and we have used also data from helium. You see that the result has not changed so much because helium forbids large values of NF. And so we still have a 2 sigma tension between this BAO plus BBN contour and shoes. What you could try to do in order to overcome this difficulty is to think of a model where your increased N effective would be generated after BBN, between BBN and CMB times. In this case, the helium bound would not apply. The overall scaling degeneracy will work fully, and you could reconcile at least all data on the background cosmological evolution. People have tried to do this by talking about a dark matter component that would decay into dark radiation between BBN and CMB times, or by putting in this early dark energy that will come to dominate precisely between BBN and CMB times. But there could be other problems still, because when you increase NF, you also have direct or indirect effect on the shape of the CMB and matter power spectrum. So if you restore the full information on the cosmological perturbation, you might get into trouble because of several things that I don't have time to detail here. Okay, so in particular, let's come back to this dark matter decaying into dark radiation, sometimes between BBN and CMB. It does pass the helium test. It's okay for BBN, but the model gets killed then when you put in some Planck data, and then you see that you are not compatible anymore with large values of H0. So you need to be more clever. And in particular, you need to put in a new ingredient that will change the evolution of the cosmological perturbation on small scales. So you see how almost crazily difficult it becomes to find a theoretical solution to the problem. It's certainly not impossible, but you need to really search very far. So people have thought about some ways, and for instance, you can invoke NF in combination with new interactions in the neutrino sector. This used to work very well. Unfortunately now, this solution is in tension with the Planck 2018 polarization data, and also with laboratory bounds on neutrino self-interactions. Moreover, this problem was not really passing the helium constraint because it had a large N effective at early times. Another option to solve your problem at the perturbation level is to put in a new interaction between the dark matter and the dark radiation that explains the N effective. In this case, you can get a fairly high Hubble parameter. Not that high though. You can go up to 70 kilometers per second per megaparsec with the models that have been currently studied. So you don't fully solve the tension, but you ease the tension. You still have a helium problem though, unless you find a good reason for which this N effective should be generated after BBN. And honestly, so far, people don't have a good explanation for that. The early dark energy model are very successful in this sense because they evade the helium bound by saying that early dark energy comes into play after BBN, and they are not so strongly constrained by CMB experiments because the early dark energy is like an effective parameter NF that goes up and down. and it fades away around CMB time, so you don't have these full problems of increasing NF at the level of the Planck data. This is why this model work quite well. They could even make some prediction that could be tested with future Planck data. Vivian Poulin is going to say a bit more on that. I would just say early dark energy is so easy. You make whatever you want with it. And is it really a beautiful and compelling explanation? I'm not sure. But if it works, and if it's the only thing that works, it should certainly be considered. Okay, so I've only talked about the Hubble tension. Bear in mind that there are other tensions. So Hendrik mentioned the sigma 8 tension that I find very interesting. Remember, there is also on much smaller scales, a small scale crisis. There are other very nice tension. Natalie didn't have time to mention, it was not the focus of her talk, but there is some kind of anomaly in the shape of the matter power spectrum that you reconstruct on the basis of the Lyman alpha flux power spectrum from Boss. I think it's very interesting also. It might be connected to the sigma 8 and Hubble tension. And there is some hope that a new extended cosmology model that you would propose to solve the Hubble tension might solve the other tensions at the same time. And thus the model might be more predictive than just putting up a new ingredient in order to solve one problem. So I will stop here. In summary, BAO and BBN alone without CMB probe independent confirmation that there is a problem really in lambda CDM. They strongly constrain solutions to the problem. There might be glows from the dark in the form of nice solution coming from non-trivial dark energy sector or the dark sector of particle physics. I will stop there. Some other speakers had a nice political message at the end. I have also a small one, maybe less important, but that I'm happy to stress. And I'm happy to take your questions.
Well, thank you, Julien, for this very didactic presentation. I think a lot of us who are observers understood a lot more the implication of BBN on cosmology. So going to the questions, I think the first one is an anonymous question, and is if Xenon found neutrino magnetic moment, can neutrino interactions arise that impact the Hubble tension?
No, up to my knowledge, if you want to solve the Hubble tension with this neutrino interaction, you need an interaction about 9 or 10 orders of magnitude higher than the normal electroweak interaction of neutrinos. And even if there is a new exciting discovery with xenon, you will still have very strong bounds from neutrino double beta decay that cannot be overcome. So so far I don't see a connection. Maybe there will be something else, but at least this new hint of new physics cannot be immediately connected to the model studied by Francis C. Racine and others. It's not the right order of magnitude.
Okay. So the next question is by Dragan Utterer, and he's asking, not clear the H0 tension is cleanly high low Z1. For example, if you take the low Z omega m prior and add the sun horizon plus BBN, you still get a low value of H0.
Yeah, it's certainly an oversimplification. It's a good way to tackle the problem, but when you deal with extended cosmological model, you often realize that things are a little bit more subtle than just this early-late dichotomy. I agree with Dragan.
Okay. Another question is, early on you mentioned that BBN approach excluded early dark energy. On slide 21, you've introduced early dark energy as a possibility. Could you please clarify?
No, on the contrary, I'm sorry if I was not clear. Early dark energy is not in conflict with BBN because in the successful models, people ensure that the dark energy field will come to dominate the expansion after BBN, after redshifts of 10 to the 8. And so they are not affecting deuterium and helium measurements. So they do not have special problems with BBN.
Okay, maybe a quick question if you make a quick answer. What is the implication for the Big Bang model if you had to make BBN consistent with the value of RS implied by the late universe H0 plus BAO?
So I'm not sure I understand the question because we are talking of rather independent things. There is no direct connection with BBN and the sound horizon. And even if you specify a model, even if you postulate a precise model, they depend on different free parameters. They have some parameters in common, like omega b, of course, or n effective. But for instance, H plays a role in the sound horizon and not in BBN. So they are independent measurements, and I don't see how you would propagate some information on one to the others unless you assume a very specific model. And even though. So no, I don't understand this question.
Okay, so maybe whoever asked the question can maybe contact you on Slack to clarify this this point. So thank you again, Julien. I'm going to move to the last talk before moving to the discussion later on. So the next talk is by Vivian Poulain.
Hi, can you hear me?
Yes, we can. Can you turn on your screen sharing so we can check?
Yes, I'm doing it right now.
Okay.
Can you see my screen and the...
Well, we see the notes for the...
You see the notes for the moment?
Yeah, so you just need to swap the screens. Yes.
Okay.
Here we go.
All
Okay,
right.
Thank you. Go ahead.
Okay, let me just move stuff because otherwise it's going to bother me. Okay, very good. So, hi everyone. So I'm Vivian Poulain, and I would like to start by thanking all the organizers because first for inviting me. I feel really honored given the panel of discussion we have and speakers we have, and also for organizing this exciting conference in those hard times. So I'm following Julien and Lloyd, and I will go on with discussing the various models that have been proposed to resolve the tension and their shortcomings, because as we said, we don't have yet one model that everyone agrees on what is nice and works. We have lots of models. In fact, here I took just a slide from Lloyd, and unfortunately, I must say that I will not be able in 20 minutes to cover all of those models. So it's going to be a bit of a bird's eye view on what I believe are the most promising resolution of the tension. So Julien already went through this. I just want to stress that I really like your way of seeing things, Julien. I have a slightly different way of phrasing the problem, which is just, again, it's actually definitions. The way I see it is that, so the way that CMB measures H0 and the way we can try and attempt at resolving the tension is that Planck measures very precisely to 0.4% precision this value of the angular scale, which is again the ratio of the sound horizon over the angular diameter distance. And the way I prefer to phrase it is to show that in the sound horizon, in fact, it depends, and that's just coming from the Hubble law relating to Freeman's law relating the Hubble rate to the energy densities. I like to say that the sound horizon depends on all the energy densities, and now I'm not talking about ratios, I'm talking about physical energy densities at early times, while the angular diameter distance depends on the physical energy densities at late times. And H0, which is the physical energy density today, only in this way only appears through this rho total today. Of course, if I write ratios the way you do it, we are on complete agreement. So once you do that, what you understand is that H0 actually tells you how far the CMB is from you. And and you can measure the way Planck measures the sound horizon is because it actually has the ability from very detailed acoustic peaks physics to, given a model, deduce the value of RS that was already explained, turn the measurement of θs into a measurement of dA, and again, given another model for the late time expansion of the universe, which usually is the same, deduce what is going to be the energy density today. And once you do that, you understand that there is a huge geometrical degeneracy in Planck, which in principle is very interesting. That is just the fact that the angular diameter distance, that was said again already, is just an integral over redshift until the redshift, actually here you see I've made a mistake. It's until, like I'm talking about Planck, so it's until the redshift of recombination, but in principle it's until the redshift you are measuring the angle to. And yes, so you can compensate a higher value of the energy density today by simply having a lower energy density in the past. And this is creating this huge degeneracy in Planck only, such that if you want to fit Planckian shoes with, for instance, a simple model such as phantom dark energy, you're completely fine. And I think this is something to keep in mind also for models that try to resolve the tension by focusing on a subset of the data. There is a very simple solution if you focus on subset of the data. The problem, obviously, is as soon as you in the BAO and Pantheon that was explained, this model doesn't work anymore. Now you might wonder, what if I have something more dynamical than just an equation of state that defines on -1? Well, we tried the most crazy thing you can do, and that is let's just have a dark energy density free to vary in beams, and we try various beams. There are lots of other people working on this and doing even more clever analysis than what we do. And the bottom line is the same. The bottom line is that you can get, a very good fit to either to both Planck shoes and either baryonic acoustic oscillation or supernovae, at this time GLA. But the problem is that the reconstructed expansion history are incompatible with one another, and when you combine them, you get this residual tension. Why is that? It's very simple to understand, and it was already mentioned by Natalie. And it's the fact that BAO and supernovae are uncalibrated at the beginning. And once they're calibrated, and BAO gets calibrated by Planck, supernovae gets calibrated now by shoes, they actually are measuring the same quantity. They're measuring the luminosity distance, the angular diameter distance, but they are actually both related in this way. So what you're saying is if the calibrator is different, is in disagreement, you're going to have a disagreement between your BAO and supernovae data now. So unless you change the calibrator, you are creating, by definition, a new tension between supernovae and BAO. And so this is what we see here. Either you decide to not, this is the plot by Lloyd, if you decide to not believe in the shoes tension, of course, there is no problem within a lambda CDM if you don't believe in the shoes tension. If you do believe in it, though, what you see is that it's better to recalibrate the BAO by decreasing the value of the sound horizon. That's what we want to do. And so it's much more informative, given that problem, to look at the tension in terms of sound horizon. And I really like this plot, again, by Lloyd and in his group. And you see that's been said already that basically all the early universe probe tell you that the sound horizon is too high as compared to the low universe probe once you calibrate BAO with the Cepheids or with the shoe. So you need to decrease the sound horizon by 10 megaparsec. Again, I said that already, but what it means physically, it means that the CMB would be closer to what you would predict in lambda CDM. So in order to counteract the fact that you would see the patch is too big, you need to decrease the sound horizon such that theta S is constant. That's just a physical illustration of what we're saying. Okay, so how do you do that? Well, the first thing to realize here, I'm showing you the sound horizon. And the first thing in lambda CDM as a function of redshift. And the first thing to realize is that it doesn't even reach the 10 megaparsec before 25,000. So you are discussing, for instance, about modifying the time of BBN, no impact on the sound horizon because the sound horizon does not even reach, again, 10 megaparsec by 25,000. So you need to insert new physics here between 25,000 and 1,000. What type of new physics? Well, you could say, just by looking at this, you can say, well, maybe I'm going to try and change the sound speed. I won't have time to talk about it. It does not work from the details of the acoustic peaks. You could change the recombination physics and try to get this star, the recombination redshift, to increase. That's something I'm going to mention. There's lots of interesting work in that field. And finally, you can play with increasing the energy density. And of course, NF would be the canonical solution. We've played with early dark energy or modified gravities. There are relations, of course, between the two. And I'm going to talk about that now. All right, so starting with exotic recombination. So back in 2018, Chang and Slosard did this phenomenological study of non-standard recombination, where they allow for a remapping of the recombination redshift following this formula with two parameters, this delta Z rec, which basically parameterize the recombination timing, and this big delta Z, which parameterize the recombination width, the change in recombination width. And it's also very nice. What you can see is from Planck temperature data, you see that there is this huge degeneracy that opens. You're just blowing up uncertainty again. It's not fantastic, but in principle, you can resolve the tension. The problem is as soon as you add BAO or anything, and here the full means polarization, typically in lensing, you see that you're driven back to be in agreement with lambda CDM. So it looks like exotic polarization recombination is in tension, but has problem in resolving the tension. However, you might wonder what happens in a real model now if I do a real model and also with the new data. It turns out that it's an interesting question. The answer is interesting, and starting by last year by this paper by Hart and Schluba, where they show that by varying fundamental constants at the time of CMB, you could at the time of recombination, you could actually resolve or relieve the tension. Never really resolve it fully, but relieve the tension. And here, it's particularly the relieval is better with the electron mass that achieves the best H0 value, and the single parameter extension reduces the tension to something like 2.6 sigma level. That's nice. However, there is something funny. That is, if you fit to Planck only, you actually find a value of ME that is smaller than the standard model, and also it goes in the opposite direction. And here, to me, that begs the question whether there could be connection with the internal curiosity of Planck, probably this L-lens tension. I think they have a comment of that in the paper, and also whether this internal curiosity could actually somewhat over-constrain some of the resolution. I put that out there just as a discussion. And I might have a comment at the end. And also, I just wanted to mention that, again, you can see when you analyze the chi-square that there is somewhat of a degradation of the fit to BAO. But still, interesting model. And along those lines, there has been even more twists, even more recent twists, again, by Karsten Damsing and Levon Pogosyan. And Levon, I'm sure we'll talk about this during the panel. And that's very nice. It's a model of what I call exotic recombination, now relying on the fact that the possibility that primordial magnetic field induced a clumping of baryons that accelerate recombination. And this model has the ability to resolve both sigma 8 and the H0 tension. That's nice. Once you do a combined fit, you get a nice detection of this clumping, something around, again, 71, similar to this neutrino electron mass that I mentioned before. The problem is similar, that once you just feed the Planck data, you have this issue that there is no clear detection. And because it's a single parameter model, as you increase the value of B, you really degrade the chi-square of Planck. Ah, yes, sorry, I forgot to say. This is one nice model because also it's not that exhaustive. I mean, this is a point that is made in the paper. The clumping factor that you need lead to a primordial magnetic field strength that is reasonable, and that would explain what we know of galactic and extragalactic magnetic field. So it's an interesting solution for sure. The problem is that it doesn't go, Planck, while the p-value is correct, doesn't see, and this is a bit of a statistical discussion, doesn't seem to favor that model. And then the question is, here we are talking about fits to Planck and shoes. What happens to BAO in Pantheon? That's something that needs to be done for such a model. All right, so moving on now with extra radiation in the early universe. As it was mentioned already, its typical way is to parameterize this extra relativistic degree of freedom by n effective at the background level. Standard model neutrinos, as you know, have n effective of order 3.046, well, sorry, of order exactly 0.046, plus, and they behave as free streaming radiation. And please, this has an impact on the way in which the perturbation behaves, and I'll come back to that later. In principle, a delta n effective between 0.5 and 1 is what you would need for a free streaming solution, for a free streaming species, to resolve the tension. And with Planck temperature data, here it was in 2015, you are actually fine. With Planck temperature data would be, again, allow yourself to blow up the uncertainty enough to be in agreement with shoes. However, as soon as you add polarization BAO, you restrict that degeneracy line. And this didn't change with 2018 data. So what can you do? Well, what if instead of adding a free streaming species, you added an interacting species? And that you can do, as Julien mentioned, by having some type of interaction. And the one nice thing that happens in this business is that this interaction between now dark radiation and dark matter in this specific scenario actually has also the possibility of resolving the sigma 8 tension. Julien talked about it already. The problem is that you end up with H0 values that are not exactly what you would like. It's around 70. But it surely deserves more study because it has the ability of going in the right direction. And yeah, I'm going to stop here. So maybe we'll have more discussion. Okay, so now the next step that you can do is, instead of saying only my extra species is free streaming, is interacting, what if all of the neutrinos are interacting? Now, what is there is a self-interaction? You can do a self-interaction, or you can do an interaction with dark matter. This has been done in this paper right here. The key idea here is a little bit different, and it comes from the fact that free streaming neutrinos have some specific effect. They lead to a phase shift, such that the peak that you actually measure, the angular scale at the peak, is a sum between the real standard horizon that you would like and some phase shift. And what you want to do is erase that phase shift by implementing interacting neutrino. Now your standard horizon has increased, and in order to compensate for that, you need a larger H0. That's kind of the short cut of the story. And there is a very nice result that has been shown also by Lloyd's group and here by Crash et al. That is that there is a degeneracy within Planck temperature data, at least, and maybe a bit weaker in polarization, without H0, you can even see it, that you can have a scenario where you have either the normal scenario with no interacting neutrino, or a very strongly interacting neutrino, an extra radiation species, plus neutrino mass of order 0.4 eV, and in this scenario, you resolve sigma 8 and H0. That's great. The problem is that there are, on this simple toy model that I showed you at least, there are strong laboratory constraints, so double beta decay, tau decay, and so on. And so the model that would actually survive seems to be a model where the heavy mediator, I forgot to say that in this model, the mediator is heavy and it needs to couple now to pass the constraint to the tau neutrino. So we will need to do a real study of the model that survives to see if such success still exists. On top of that, I want to say that the polarization data seem to disfavor the strongly interacting mode, but there are not yet any 2018 studies, so I don't know if that's still the case. You can relax the assumption that you have a heavy mediator and have actually a light mediator, and this was done by Escudero and Witte, so it's a different model. I kind of simplify a bit by saying just you change the mass. At the end of the day, the bottom line is this model is interesting because you actually might be able to relate now the Hubble tension to the way in which neutrino acquires their mass. And again, you have a similar, so once the story is that if you do again a fit to Planck only, you relieve the tension, but it's only once you include shoes that you seem to have a clear detection of your particle and the extra ineffective that you need. I do want to mention that here it seems to increase the sigma tension, but in this paper they did not include the neutrino mass like before, and it would be interesting to reanalyze this type of model now, including neutrino mass in the analysis. Moving on in my last 5 minutes to something I know a little bit better, and those are the early dark energy models, and I'm connecting them just very quickly. I just want to say that in principle, those models could be related to modified gravity, at least with scalar tensor theories. Of course, there can be differences, but please, mainly what I want to say is that there are lots and lots of models on that on the market right now, and I'm going to focus on on the one that I know the best, mine. But please, there are lots of interesting studies, so have a look at them also if you're interested. The bottom line looks like this. The basic idea looks like this. So it's that there exists an additional scalar field that is frozen due to Hubble friction in our model, and eventually the Hubble rate drops below the mass of the fluid, and the fluid starts rolling. So originally the energy density is frozen, then the field starts to dilute. And we played in this study with an oscillating toy potential, which looks like an axion, and we put an exponent here. I'm not claiming that this thing is existing, but I am claiming that this is very nice. This phenomenological potential is very nice to extract properties about the resolution. And I think this is an interesting approach. I fully agree that we should also have great theories to try to resolve the tension, but the bottom-up approach has some virtue. I'm going to try to argue with that here now. So there are 4 parameters in this phenomenological approach. There is the fractional energy density of the field at the peak, at the critical redshift. The critical redshift being the time at which the field starts to dilute. Then there is the equation of states, which for us is related to this n. And the equation of states governs how fast the fields dilute. And finally, there is a degree of freedom describing perturbations. And once the potential is fixed, it's actually governed by the initial field value in our model. Okay, so I wanted to show, because this was discussed, I've seen papers about this. First, the result just with Planck. And this is what you find when you play just with Planck. So when you play just with Planck, with the 3 parameters model, this phenomenological model, what you find is the red curve here. So you don't see any detection of the ED from Planck only with the 3 parameters model. You actually have a constraint at the level of 9%. You have a delta chi-square that's interesting, but what I wanted to argue here is, and what we argued in the paper, is that this is actually also coming from the choice of prior we made, because there is a strong chi-square degeneracy between lambda CDM and early dark energy within Planck data. This is what I was trying to highlight here, where you see that actually the chi-square of the ED is slightly smaller than the one of lambda CDM. And so basically what happens it's that if you put your fraction of dark energy to 0, you end up having a huge degeneracy here in the log ZC theta I plane, due to the fact that FED equals 0 exactly corresponds to lambda CDM. And once you project in 1D, you have these strong constraints. In fact, if you knew the model, the best case scenario, you would probably know the model. You would know what is the critical redshift, you would know what is the initial field value. So let's play the game, and I do that here just for illustrate that if I knew these parameters, and of course here I'm biased, so I do it at the best field value, but it's not a completely stupid game. It's just to show you that you can find this strong degeneracy that was mentioned before. The thing that you win, and that's kind of accidental, is this -5 delta chi-square actually leads to the ED to be detected by Planck. But of course, this is completely artificial, given that I knew where was the best fit. But again, in this game of trying to learn things, it's not so stupid. Then you can add a prior on H0. And if you add the prior on H0, you find this posterior here. You detect, you learn about the critical redshift that I mentioned before. And you also detect something, you learn something about the initial field value close to the potential, close to the, sorry, the initial field value, which means the shape of the potential close to the maximum, close to the initial field value. Sorry, let me skip. Once you add BAO in Pantheon, I just wanted to mention that nothing bad happens to this model. So that's the one nice thing. But there are catch in this model. And yes, and the last thing that I wanted to say is that on top of that, it's been shown by Lin et al. That you can constrain the perturbation. However, there are bad things in this phenomenological model, and that has been that we have pointed out, and that was pointed out as well, and that is that the sigma 8 tension in this model increases. The fun thing is that it does not increase because of the EDE itself, in fact. So if you look on the right side, I plot the nonlinear and the linear matter power spectrum in various cosmologies, and you see that the EDE increased the amplitude at small scales, and it's not the EDE, it's actually coming from the shift in omega CDM and NS that were required by CMB data. And if you fix omega and CDM and NS, actually the EDE actually has the opposite effect, it reduces the amplitude of fluctuation. But once you do that, because of that, there are potentially strong constraints from large-scale structure. I just want to mention that with the consensus BOS data, you actually have weak constraints, relatively weak constraints, but it is true that the full shape breaks completely the degeneracy and would exclude these models of dark energy that exploit like this degeneracy. All right. So since I'm running out of time, let me just mention that that one thing that is going to be interesting in any case is going to be to look for signatures of this model, and that goes beyond trying to. I think it should be done in parallel of testing, improving the accuracy of H0 measurements. That is, all of the models that I briefly discussed have signatures that should be seen in future data, whether it's CMBS4 here, or even large-scale structure. We are working a lot on, and I unfortunately didn't have time to talk about this, but people that know better than me about large-scale structures are trying to make predictions for that using this ED cosmology. So I think one thing that is going to be very important, if the Hubble tension is true, is to find deviation from lambda CDM. It's something that has nothing to do with H0, and maybe S8 is one thing. And since I'm out of time, I'm going to let you with my quick and biased summary of the H0 tension resolutions that hopefully will trigger some discussion.
Well, thank you, Vivian, for this very, very dense talk and with many possible solutions. So going to the questions, the first one is an anonymous question, and it asks, are any of your arguments changed if you use the holy cow constraint instead of shoes?
I don't think so. Well, it's yes and no in the sense that maybe it's going to have some constraining power in helping in pulling up. So it might help. The constraining power of the shoes likelihood is important to pull up this type of solution. So in that sense, yes, but I don't think it's going to constrain more the solution.
The second question is still an anonymous question. How would varying physical constants fit in this problem?
Additionally, if you do it additionally, I guess, or, well, I mean, I guess you could imagine combining several solutions, and that is something that has not really been studied, so I don't really know. Otherwise, I think I already talked about varying fundamental functions.
Okay, so maybe a last question before we move to the discussion session. How would you say the Hubble constant problem is more meaty for theorists than the cosmological constant problem?
The Hubble. Well, right now, the way I see it is that the Hubble tension problem can be approached by a phenomenological. Well, yeah, it still needs to be approached through this phenomenological way. So it would be interesting. Lambda CDM at the end of the day is also a phenomenological model and still fits the data. And from the parameters, we now try to make sense of them. I think that's what we need to do first with the shoes. That's my approach, at least, is try to see if we can capture the dynamics. And in that sense, there is a lot of work for phenomenologists. And then once we understand what is required, we can decide what we can work, or at least find guidelines to build models. Then are they connected? All problems might be connected and we just are not clever enough to see them.
Okay, so there's still one question. I don't think maybe we have, no, there's another question appearing. So maybe you should go on Slack and check out the question to answer, and then we're going to move to the discussion. So I will ask all the speakers to turn on the camera, the panelists as well. I'm not so sure who is going to chair actually the panel. Yeah, and also, yeah, I'm reminded that there is a Slido actually also for the panelists. Right now, there is no question there, but okay. I see, I'm not sure.
So do you want to share it, Antoine?
Yes, I will share the screen. I'm just checking that I think all the speakers are here. What's going to happen if I do that? Okay, so this is for you guys to discuss. So I'll let you, I don't know who is the chair of your discussion. Is it you, Levan, or?
I'm happy to sort of chair in a gentle way, just to say that we planned to make sort of 3 minutes opening statements, all of the 4 panel members in alphabetical order, and then we'll open the floor for discussion, and hopefully we'll have about 18 minutes for questions and answers. So okay. I invite Pablo to start.
Yeah, hi. I actually think Matthew would have been first, but I'm happy to go. Do you want to start? Do we have the slides? Yes,
oh,
so
sorry.
Do you want Matthew to go
I made a mistake.
first?
I'm sorry. It's Matthew. I'm sorry. I'm not.
Okay, so I'll go first. So
yeah.
I just wanted to make a couple of quick comments about testing the BAO scale before I show a little bit of some interesting future observations. So we've heard a lot in theoretical talks today about solutions that largely focus on the maximum physics gain, trying to get the most new cosmological physics out of the data. And I must admit, I would be tempted to focus instead on those with minimum physics pain. So as we've heard, if you have to pick one parameter to fix the problem with BAOs, it's the sound horizon scale. And the tricky part, as we've heard in enormous detail, is managing to reduce that by something like 5 to 10% while still maintaining consistency with the CMB and all the other observations we've been hearing about this week. And of course, ideally, any solution would not only be consistent with lambda CDM, but would also try and fix other problems like the S8 tension as well. And so something like early dark energy is a maximum physics gain type solution, whereas something like primordial magnetic fields would be a minimum physics pain solution in these terms. Another comment I wanted to make is in the next few years, we're going to have significantly more precise BAO measurements in redshift spin spanning most of the redshift range from 0 out to the CMB. And we can then ask ourselves whether these follow a lambda CDM expansion history over this whole range. If we replicate lambda CDM over that range, then that would tend to suggest an error either in the CMB determined BAO scale or of course in the distance ladder calibrations to resolve the Hubble constant tension. Similarly, over the more limited redshift range where you've got both the BAO and the supernova distances, you can actually look at the ratio of those and see where it's fixed or evolving with redshift. So that's just a couple of general comments. If we could have the next slide. Someone got control of the slides? Yes, thank you. So we heard about the beautiful DESI survey, which is going to be spectacular. There's another similar survey in the southern hemisphere called TAIPAN, which I'm leading. That's going to survey about 2 million galaxies at a mean redshift of 0.17 over more than a cubic gigaparsec. And from our detailed simulations, we expect that in the first year and a half, phase 1 of our survey will get H0 down to 2% and just below 1% over the full 4-year survey. That means that we'll be doing about 5 times greater precision than the existing 6-year survey and comparable to DESI on a similar sort of timescale, but with an independent volume. So that'll be a nice independent check. Final comment I wanted to make on the next slide is we've been hearing about the S8 or sigma 8 tension, We heard about it from weak lensing and other sources. I'd like to point out that you get a similar result also from peculiar velocities. A recent result, which is about to appear in Astro PH from Khaled Saeed and others, looks at about 16,000 galaxies from the 60F and SDSS surveys, and you end up with a constraint on beta, which can be translated to a joint constraint on sigma 8 and omega m. And as you can see, as with other results, what you find is that these peculiar velocities give an estimate of sigma 8 that's lower than that expected from Planck at any given omega m. So those were my comments.
Okay, thank you. Pablo, please.
Yeah, thanks. So I wanted to also make some remarks related to what we just talked about. So first of all, I wanted to something that was already mentioned in several talks, both earlier in the week, and also Julian particularly mentioned it today, which is basically the fact that even there are several works. So we had a paper, but I know Licha, who's here, and her group had a similar paper using Gaussian processes, where you can show that if you as long as you have the sound horizon from Planck or even from BBN, even if you relax the assumption of lambda CDM at low redshift, you still recover with BAO and supernovae a high H0, which to me is indicative that unless we have some really surprising physics at low redshift, that's not where a theoretical solution would live. So I think to me that's indicative that if we want to solve this from a theory perspective, we need to look at a theory that lowers the sound horizon. And that's kind of one of the main features that we have to look at. So if you look at the next slide, so I summarized some of the things that such theory would need to fulfill. So those things being, for example, lowering the sound horizon, obviously, but also we would have to preserve the structure of the CMB, right? We don't want something that produces a much worse fit to the CMB. That would be indicative that is not a good model. We need consistency between BBN and the light element abundances, like Julian mentioned as well. And we do need also to pass some kind of model comparison test, which is it relates to what was just mentioned of the complexity, or I don't know, physical pain, I think you called it, where we cannot just keep adding parameters until we solve the tension. We need to also sort of keep some kind of measure of simplicity versus and related to that, I think it was mentioned at some point as well during today, and I think it's not talked about that much, that even if we found a model that only adds 1 or 2 parameters and solves all of these tensions, it is important to sort of, we are physicists and we need that model to also be predictive. So it wouldn't necessarily be enough that we solve the tension for us to believe that model, right? We need a model to be predictive and to make some kind of prediction and then confirm that prediction before we can actually believe that that is the true physics of the universe. And if you move to the last slide, it's kind of highlighting the importance of accurate BBN measurements. So that shows the 2 existing estimates on the baryon density from BBN. One's called empirical, one theoretical. I don't know much about the details of where these numbers come from. It's not my field, but I know that they are most definitely in tension themselves. And the plot on the right is from a paper where it shows DESI forecast, with each of these numbers, and you can see how it, for the current experiments, is not a problem. But as we go to DESI precision, which Natalie talked about a lot, it will be a very exciting survey. But as we go to that precision, it will depend on our BBN measurements. It will be quite sensitive, in fact, to our BBN measurements, how we can constrain H0. So I think it will be very important to get an accurate BBN, perhaps something that we don't talk about as much, to get a reliable and accurate BBN measurement before we start looking at these things. And I'll leave it to the next panelist.
Leron, you're muted.
Sorry about that. So I just had a couple of sort of general points that some of them were voiced and some perhaps haven't. So it's quite clear from the talks this afternoon and earlier that it's very hard to get to shoes-like number 74 and keep the agreement with CMB and BAO. And most of the models that tend to come close to that, they do it at the cost of blowing the uncertainty in H0. Probably not all of them, but those that actually get to 74 tend to do. And so I just don't think, in my opinion, I think replacing the H0 tension with unknown H0 is not necessarily a solution. Also, just to make a point that sometimes we perhaps pay too much attention to sort of minor differences in chi-square when they're below 1 sigma. And that echoes the points made earlier that maybe we should look at other ways, like maybe maximum physics gain, minimum physics pain, or even statistical measures like the probability to exceed when assessing, comparing models. And then my last point before I move to the next slide is that there are all these tensions both within some data sets and between the data sets, and they're not necessarily all significant, but there are a few of them. And it's going to be quite a challenge to find a model that gets to 74 and doesn't really violate chi-square for one of those. So if we find a model that actually predicts H0 around 70 with no tension with any data set that accepts shoes, should we sort of look at it very seriously? And I do have an example of that. Can I have the next slide? Can I have the next slide, please? So yeah, so this is an example of the, this baryon inhomogeneity model, baryon clumping model. Here, the baryon clumps are induced by primordial magnetic fields, and that tends to speed up recombination. So I've broken this model according to Lloyd's criteria for what would make a good model X. So it doesn't resolve the H0 tension, but it gets close to it. So in this plot, BAO is included. And you can see that once BAO is included, it doesn't really let H0 to get higher than about 70 or 70.5 at the central value, but the uncertainty around H0 is quite compact. So it sort of makes a prediction, and it still resolves the S8 tension. Also, regarding the BAO point, we haven't published our BAO results yet. So this is still an evolving issue. This is a preliminary plot. So maybe it was a bit premature to say that BAO completely prevents this model from materializing a higher H0. But in terms of being compelling and beautiful, I think there is, it fits in that category very well. There is a lot of evidence for primordial magnetic fields coming from intergalactic, from cosmic rays and clusters, etc. And this model actually makes a prediction. So if the magnetic fields are there and at the level enough to solve the H0 tension or get it to around 70, then we should see them in STEAM-MB spectral distortions and most likely in cosmic rays as well. So thank you.
So thanks. So I would like to summarize some comments, which I think is interesting for this conference. So mainly those you know, but this I want to stress. So the present CMB tensions or discordance are mainly of three types. Say the H value up to sigma, say the amplitude of fluctuation, sigma 8 is 8, I mean up to sigma. We have seen from previous talk that it could be more than to sigma. And this is depending on tau at the reionization, strong degeneracy with dark energy, and the internal consistence, as we know, the IL lensing, depending, I mean, up to or more than 2 sigma, depending on the modeling of foregrounds and again of tau reionization, mass, effective mass of neutrinos. And this mainly affect the test of lambda CDM extension, but not lambda CDM. The origin of these reasons or discrepancies, of course, is trivially to say that it could be from the different measure origin from different measurements, the errors, the systematic, the different methods, the scales, or truly physical cosmological effects, or a combination of both two, but in any case, we need to understand them. The independent different set of measurements at different redshifts, scale, techniques, objects determine the two different set of values of H0 from, say, the early and late universe measurements is for me convincing enough to understand that the H0 discrepancy have a true physical origin, a cosmological origin, and this is the vacuum cosmological energy, which is just dark energy today, but is vacuum energy in general, in the early universe in particular. Vacuum energy is everywhere in the universe with different physical properties, from inflation and even before inflation, until today dark energy, which is the today classical cosmological gravitational vacuum. So if I can have the next slide, I mean very, very quickly, if I have time. So this came from the fact that the universe the universe undergoes different phase transitions, and inflation is one of them, and start from a quantum, really a quantum vacuum. In fact, our fluctuations came out of the vacuum from inflation, then to semi-classical regime, and then, which is more or less grand unification in the force of particle physics, and then radiation dominated, so the universe classicalized till our gravitational classical vacuum energy. The key concepts are the vacuum cosmological energy is related, connected with the Hubble constant. I mean, it's the main effect. And the main concept now, which I am understanding, is the gravitational entropy, and with that the arrow of time. And the gravitational entropy in any of the regimes of gravity, and so of the regimes of the universe, from the very early and quantum to semi-classical and classical, determines the arrow of time and is a container for the content of the universe, which are all the other effects we are seeing. I stop with the next slide, please, and so this came with just as a summary for numbers, but I mean, the H0 problem I have not still developed, and is very recent. And this touch with the problem of the cosmological constant problem, or the mix match between quantum and classical gravitational vacuum energy. And so this allows to precisely interpret the classical quantum dual of each other, and precisely the difference of this number, the mismatch of these big numbers, must be like that because the universe is in different physical states, in very huge different physical states, from the very early to the late universe today. So understanding the link of that is connected with the H0 problem, and mainly another problem. Let us, I finish now, let us recall that lambda CDM is more than a set of 6 parameters, or even more with if we add tensor fluctuations. Lambda CDM has behind the theories or models, some of them well established, but in there, some of them we need to be extended or modified. And these pieces of lambda CDM must be understood in their own range of validity. And so the model must be extended in the sense of physically understood in the link of the early to the late universe. And
Okay,
I finish with that. The fact that there are more and more precise measurements are showing, and this is what I mean, I am looking for the data, are showing more discrepancy between the tension, if you want, between the late measurements coming, I mean, in this case, H0, because it's a real key parameter, or
okay,
lambda.
no, I think
I
we are
finished.
well above 3 minutes. I think it's
Thank you very
like
much. It's
7.
my last.
Thank you.
Thank you very much.
Yeah. Thank you for all of that. I didn't plan to chair this, but I suspect I could first ask all the panelists and the invited speakers if they would like to propose a question.
Yes.
Yeah, please go ahead.
There are plenty of questions on Slido. Maybe we should.
Yeah, I agree. It's a good idea. So I'm happy to read them out. So the top question at the moment is, what is the Taipan 2% measurement expected to be calibrated by?
So Taipan is just like all the other BAO surveys. Essentially, you're basing it on either the CMB or the BBN calibration for the sound horizon scale. Alternatively, you can think of it as assuming a cosmological model and then testing consistency at 2 different redshifts, the CMB redshift or the BBN redshift and redshift 0. But it's the same as any other BAO survey in that regard.
Thank you. So the next question is from Jeremy Mould. Is minimum physics pain another term for Occam's razor?
Well, other people might like to answer that, but my own answer is it's not quite the same. Occam's razor might say you could introduce one parameter in 2 different theories and it would be equal multiplying or equal addition of entities. I'm actually looking also at the aesthetics of it and whether one is happy with the change one's making to the physics. So for example, I know magnetic fields exist, so I feel more comfortable adding early magnetic fields than I do introducing some new early dark energy that I don't otherwise know about. But that's a matter of taste. And I'm happy to let other people comment on that one.
So anyone else would like to comment on the minimum pain?
So I find it interesting that people talk about minimum pain, elegance, beauty. And so I'm an observer and we try to make ourselves, pretty much immune to our preconceptions, right? We always do blinding. We don't look at our data really till we're really sure that we don't change anything anymore. And then on the theoretical side, people talk about beauty, pain, and so it just doesn't feel right from an observer's point of view.
I mean, if I can make a comment, I mean, in principle, I agree, except that we live in a lambda CDM cosmology where 95% of things we don't even know. I mean, I completely agree. I mean, I like the way you phrase it. So I think often there is a problem between the fact that we introduce parameter, for instance, in the model, is not necessarily an Occam's razor problem, because we are just introducing it. What I'm trying to say is it's the difference between number of degrees of freedom and number of parameters, and that's what I'm trying to explain badly. But I would love. I mean, magnetic fields is a very compelling alternative. There's no problem. I just want to say that in the business of beautiful, we should just remember what we take as our baseline standard model. That's all. Like so in the end, what I'm trying to say also is playing with dark energy. Playing with early dark energy or dark energy and so on might just be opening a door towards trying to understand what are these lambda and CDM. That's all.
Thank you.
If I may, I think.
If I can.
Okay, so I finish quickly. So indeed, beauty is a nice concept. Of course, the answer about beauty will always depend on whether you come from particle physics, general relativity, astrophysics. It's a bit subjective. I think the key words here is predictivity, really. If you have a theory which can solve several tensions and make non-trivial prediction that will be tested in a few years, maybe in another field or maybe still in cosmology with a better observable, then I think it's a very good, it would be a great success. Of course, it's not obvious that we can reach this.
Yeah. So I'd like to move to the next question with your permission, which is actually to me. It says, how does the shape of the primordial magnetic energy spectrum affect the value of H0? The shape of the spectrum does not play a role. What plays the role, what's most important is that you have sufficient energy in the magnetic field on 1 kiloparsec scale. What happens on larger scales doesn't matter. So it's the 1 kiloparsec scale magnetic field that matters most. But the shape of the primordial magnetic field spectrum will be important for the subsequent evolution of the magnetic field. So it would play a role in predictivity, in what you predict will be seen in, for example, cosmic ray data. So
Levin, I had a question about that. I mean,
yeah.
We also have a very different problem in galaxy evolution with generating supermassive black holes and indeed galaxies at very early times, which is quite difficult to explain. Would the clumpiness in your baryon distribution induced by the magnetic field help alleviate those problems as well?
That's a very good question. Good question. It was asked sometime before. Most likely, as far as we know, it doesn't help, but it's definitely a good question to think about. Yeah.
If you allow me, I want to comment on that. Primordial magnetic fields and magnetic fields in general are very interesting in its own right. Now, it's very difficult to generate primordial magnetic fields, in particular inflation, which is the origin of our fluctuation, which we see in the CMB spectrum. I mean, not exotic physics. So inflation do not produce primordial magnetic fields. It can be, I mean, it's the conformal invariance of Maxwell and de Sitter or de Sitter inflation, and so in the same way, the same reason why we don't see vectorial fluctuation, primordial fluctuation. So there are different mechanisms, but you need to work around. It's very interesting in its own, and for sure for testing the polarization and so on. I mean, large correlation lengths of the field. Now, Faraday rotation and so on. Now, is that for H0 so relevant? I don't think so. I think that it could adjust the problem, but not the main problem. All is how to simplify the problem and start from the essential in the case of H0. And so it goes in the right way, because any force or any effect that goes against gravity, as the dark energy, for instance, is reducing the horizon, and in particular the sound horizon, and so you are in the right direction, even if it doesn't solve the problem, as you already said. So primordial magnetic fields, very interesting issue to study. I mean, a lot of future, but is not the main reason of the H0 problem.
Okay.
And also I attach to the same reason I just to the same argument all these models, because there is a lot of confusion if we mix all the ingredients, the essential and the not so essential one in this. I mean, the problem is already difficult. And this dark matter disintegration or is the same, I mean, of the NF is the same, because if you have some charge which, or some radiation set, which goes against gravity, you have in the direction. Yeah. And definitively, I will not put on the same level of predictably of the fundamental, all these variation of constant, fundamental constant, modified gravity, and so on.
Norma, I hate to interrupt you, but I'm sorry, but we need to cap the length of the individual text. I'm really sorry to be in this position.
No.
I wanted the moderator.
The discussion is like that.
But if there is time, let's take a couple more questions, not about magnetic fields. Does the diffuse matter recently verified by FRB observations affect the constraints from CMB polarization? Anyone, any takers?
What, could you repeat, please?
The question is, does the diffuse matter recently verified by fast radio burst observations affect the constraints from CMB polarization?
I guess that would be a question for someone from the plane collaboration, no?
Yeah, I don't know if,
I don't know the answer.
So maybe we'll leave that for Slack. Somebody maybe will eventually reply on Slack. So the next question maybe is for Vivian, is what's more painful, introducing extra dark energy events or allowing for some curvature?
Well, if curvature was working, obviously it wouldn't be less painful. There's no doubt. I mean, obviously. The problem is, of course, that it doesn't work. So given that that's not shown by the data, what can I answer? Yeah.
Okay. Okay, we can move to the next question. So from Louis Marmet. So Nathalie commented that the 150 megaparsec scale assumes Planck cosmology, but supernovae give 130 megaparsec. Could this point to new physics in the local universe? The question is for Nathalie.
Well, I'm not even sure it's for me. Taking H0 from supernovae does mean that it gives a sound horizon of 130 something megaparsec. Now it's the same tension as the one we've been discussing. It's so the theoretical answers to that issue is not found yet, and it's one of the many approaches that Vivian and others have introduced.
Okay. Does anyone else have additional insights on the panel?
I believe there's a paper, can't remember who was on it, that kind of phrased the problem like that, being if we assume H0 to be 74 and we kind of climb the distance ladder up to the sun horizon, and they basically like
right.
Like Natalie said,
the most recent approach is this Taylor et al. Paper that does that exactly. I mean, the goal is you can recast what you know from H0 into R. I think that's the answer to that question. So no, there is no, it does not point out to new physics in the local.
Okay.
I think we need to keep open mind, attaching some phenomenological set, physical approach, attaching to data, but I mean, let us about what you will comment about exotic, that early dark energies, exotic and so on. But let us recall that the universe, we lived many of us in a universe in which we didn't know that existed dark energy or that existed the present acceleration. So that is, we need to attach to fundamental physics and to data, and keep open mind, because long as CDM, I mean, it's clear that it's a model which needs to be completed, improved, and some pieces changed.
Okay. Thank you. So the next question, if we have time, I think it could be for Julien maybe, or Nathalie. Could you clarify similarities and differences between the BAO and large-scale structure measurements from an observational point of view?
Well, large-scale structure measurements is just a very generic word covering many things. So for instance, if you measure the galaxy power spectrum from BOSS, or in the future from Euclid or LSST, you have an amount of information. And one of the information is a measurement of the BAO scale. It's just contained in the total. And so far, people are a bit scared of doing a full modeling of the matter power spectrum at the theoretical level, including nonlinear uncertainties. So they only extract from their large-scale structure data the BAO scale. But in principle, you can extract more. And I mentioned this paper by Phil Cox, Ivanov, Simonovic, and Zalariaga, in which they do it very nicely. So the information they retrieve from the matter power spectrum is the BAO scale, plus all the details of the shape which have additional sensitivity to cosmological parameters. So it's just one is more global.
Okay.
Yeah, just one word to add to what Julien just said. I mentioned that Desi relied upon two techniques. BAO is one, and BAO is very straightforward in a sense, since it's just measuring a position, a peak, or a wiggle in a Fourier spectrum. Whereas we're also relying upon redshift space distortions, for instance, which is exactly what Jan described. It's the full shape of a power spectrum, not just the position of a feature in that power spectrum, but the shape and amplitude of the full power spectrum as a function of scale. But that includes a very good understanding of the nonlinearities that come in, but they carry a lot more information. And so the most conservative approach is BAO, but there's a lot more to get out of it, and redshift space distortion is one of them.
Okay, thank you. So if we have time, we can maybe take another. This is a question for Julien. What about changing CMB temperature?
Yeah, I mentioned it very briefly. So we wanted to study in this recent paper, but probably the person who asked the question. So we wanted to study in which degeneracies this T0 temperature is implied. So if you make T0 the seventh free parameter of lambda CDM, because you don't believe phi ras, for instance, you open up a new degeneracy. And for instance, you realize that the constraint on T0 coming from Planck alone is quite loose. There is one, but it's quite loose. And with Planck data alone, so you are allowed to go through this degeneracy and obtain a very large or a very small H0. However, as soon as you combine Planck with BAO, you are driven back to the standard value of the CMB temperature today. It's a bit like omega K. If you don't have BAO, Planck is not giving a good measurement of omega K. There is a geometrical degeneracy. But when you put back the BAO, you are driven back to a nearly spatially flat universe. So it's a bit the same. And at the end, I don't think you can solve the Hubble tension by playing with T naught.
Thank you. And if there is a bit of time, I'm going to take take advantage of my role of impromptu chair and move the third question to the first place, which I kind of have myself. The question is, minimum physics pain would seem also to be relieved by the TRGB distance scale and the value of H0 equals 70. Are we focusing too much on shoes? And maybe I would add that indeed the other sort of
yeah, I mean, if I may,
yeah.
I mean,
Yes, please.
Personally, I said shoes, but I think I always meant to say the combination of shoes plus a bunch of stuff. And I think what Adams and a bunch of stuff and all the other measurements, sorry for and all the other, so what you can do surely is say, if I don't take shoes and I combine my TRGB with all the rest, what happens? And the answer is you still get much higher than 70. I mean, that's the, otherwise, what you can say is if I just believe TRGB and throw away all the rest, yes, okay, but then that's another problem.
Oh, all the other H0 determinations have much larger uncertainties. So
no, but I mean,
that's with the smallest.
I mean, there are lots of plots showing that even without shoes.
But the tension is the strongest with shoes. That's what pushes it above 4 sigma. It's shoes.
That's just not true. I mean, you take holy cow and you combine with TRGB, you already have a strong tension.
I see.
That's what has been shown by the first lines. That's the problem. You cannot. I don't think it's easy to just say shoes has a problem anymore. At least that's my opinion. Okay. But I agree. I mean, in principle, if the solution is 70, in all of the model that we have tend to point to something like 70. So I don't know.
Well, I think this is a very interesting discussion, but I think we need to move to Slack maybe to have a discussion. I see Pablo, maybe the last word in a few minutes.
Yeah, well, no pressure. Yeah, I just wanted to point out that I think it's a good question because we've been talking about theoretical solutions, but I think it's important to keep in mind that it is just as likely, if not more likely, that there are systematics in either in Planck, in shoes, and that we are doing something wrong in the experimental side, because there are still a lot of things that we don't understand. And there are things we could be doing systematically wrong in all of our experiments. So I think the question kind of does show something that's very important to point out, that is that it's not necessarily a theoretical thing. We want it to be a theoretical thing. It would be more exciting if it was, but it could very well be a systematic.
In any case, the tensions are there, and we need to understand also theoretically and physically. And the lambda CDM model, to which H0 is one of the parameters, these are connected. The lambda is connected to H0 and others of the parameters. And we need to clarify the issue. We cannot escape by saying it's systematic. As I said in my first statement, I think that the body of the set of measurements and different techniques, I will not repeat. I mean, other speakers already talked. I mean, in the other session, Adam talked, for instance, and it's very compelling. It's very robust. And of course, we need to understand also the systematics and so all the measurements. But it's not just to play. It's not just to play with dark energy. We don't understand completely dark energy. And it's completely connected. We don't understand the early universe in all. So we need to keep really with the effort and the physical effort, I mean, as a theoretician, to be at the height and at the precision of the forthcoming and present data. Thank you.
I think we will finish on these words. Levon, if you want to add something as the chair to conclude the panel.
Thank you. I was a chair only in the executive sense, so I'm happy to let everyone relax.
Yeah, I think this was a very lively discussion. I would like to thank all the speakers of today for the quality and the insightfulness of their talk. Also for the panels, for the
thank you,
panelists for the livelihood of the discussion. And I would like to invite also everybody to turn on the camera to say bye and to reconvene tomorrow for last day and hopefully still lively discussion. So
thank you.
Bye.
Thank you. Bye, everyone.
Enjoy your evening,
Thank you.
morning,
Thank you.
night.
Bye.
Ciao.
Bye.
Bye, thanks.